In this video, we are going to solve the same example we solved in our previous problem, but this time we're going to solve this using a different method, which is a lot quicker than our other method. So here I have my free body diagram where I've solved for the reactions at both A and B. You can see the previous video to figure out how we did that. And I'm going to start my shear diagram. Our shear diagrams always start at 0, and they should also end back at 0. Same for our bending moment diagrams. Everything starts at 0, everything ends at 0. So here at 0, at x equals 0, I have a positive force of 15.3. So I have this positive 15.3 force going upwards. So my shear diagram is going to start at x equals 0 with a positive jump of 15.3. Now between, we should label these, so this is A, B, and C. So between points A and C, there is a distributed load, so I need to use that equation where the shear at C minus the shear at A is equal to minus the area under the load curve. So the area under that load curve, I have 2.5 kips times that distance was 6 feet. So the shear at C should be minus 2.5 times 6 plus my shear at 8, so plus 15.3. So it's going to be 15.3 minus 2.5 times 6, and that gives me 0.3. Now because my distributed load is flat, it's straight across, my shear diagram is going to be linear. So I'm going to have a straight line going from 15.3 to 0.3. You might want to use a ruler here so it's nice and clear that that's a straight line. So it's 15.3. So next, also I'm going to highlight that this is what caused that. Let's kind of color code this. So next in my plot, I have a downward force of 12 kips on my beam. So my shear diagram is going to go down 12 kips. So I'm going to go from 0.3 to negative 11.7. And if we're color coding that, that is going to be highlighted blue right there. We're going down because of that downward 12 force. So next I have between C and B, there's no distributed load. So my shear diagram is going to be straight across. Another way to show that is the shear at B minus the shear at C. It's going to be minus the area under the load curve, which there is no load curve, so VB equals VC. So that's going to go straight across to negative 11.7. And lastly, I have my upward 11.7 force there at C. So my shear diagram is going to go up 11.7, and it's going to end at 0. So these problems are really great because it allows you to check your answer. Note, just because it ends at 0 doesn't necessarily mean it's right, but if you've checked your work otherwise and it ends at 0, it's a pretty big indicator there. So let's move on to our bending moment diagram. We're going to start at 0. We have the bending moment at C minus the bending moment at A. It's going to be the area under our shear curve from A to C. So that's going to be that little rectangle, 0.3 times 6 plus the triangle 1/2 15 times 6. So MC is going to be, MA is 0, so it's just going to be 0.3 times 6 plus 0.5 times 15 times 6, and we get 46.8 kip-foot. So 46.8. Our distributed load is flat. Our shear diagram is linear, so that means our bending moment is going to be a parabola. Because the slope of the shear curve is negative, that means our parabola is going to be facing downward. So we have a downward facing parabola from A to C in our bending moment diagram. Now we're ready to do the second part of our bending moment diagram, which is this section right here. So we're going to have the bending moment at B minus the bending moment at C is going to be equal to the area under that load curve, so it's minus 11.7 times 4. So we have MB is going to be 46.8 minus 11.7 times 4. This should be 0, but let's plug it into our calculator to make sure. And we get 0. So there's no distributed load, which means our shear diagram is flat, which means our bending moment diagram is going to be linear. So that is the same example that we've done, solved using a different method, so using the relationship between the loads, the shear curve, and the bending moment curve, to solve the problem a lot quicker than the other method. Use either method on your homework and tests, but as you get more comfortable, I think a lot of you might end up favoring this method because it can help you solve really, really complex problems very, very quickly.